Today I'm speaking with Dave Millure, Senior Vice President of Sales and Marketing at Metglas, who is going to talk to us about the evolution of amorphous metal technologies and how these developments help with energy sustainability efforts. Dave, please tell us a bit about the history of amorphous metal and how the technology has developed over the years.
Sure. Amorphous metal was first produced in a Caltech lab here in the United States in the early 1960s. And then in the 1970s, the U.S. company Allied Signal developed the first cost-effective process to make it in really commercial volumes. This method was called planar flow casting. This is where molten metal flows through a slot in a nozzle onto a spinning wheel, and the metal freezes instantly at about 1,000ths of an inch thick. It comes flying off at about 60 miles an hour. And we catch it and take it over to a winder where we put it up on big spools. And this is the first time this was ever done. By freezing it so fast, running so much material onto such a small puddle, this freezes the atoms before they can arrange in what they really want to become, which is a crystalline structure. So in the way we do it instead, they're stuck in sort of an amorphous or random structure, so that's why it's called amorphous metal. And Allied Signal adopted the name Metglas, and that means metallic glass. And this name is really sort of the Kleenex version of the amorphous metal world. Everybody talks about Metglas synonymously with amorphous metal. The next big development was in the mid-1980s when the U.S. government, through their Electric Power Research Institute, or EPRI, they saw the energy savings potentials for this iron-based amorphous metal for electricity distribution, where the distribution transformer, which is the last transformer in the distribution grid, hanging on the poles or on a pad in front of your house, distribute the energy, the electricity to the end user. And they provided funding, EPRI did, to Allied Signal, and we were working with GE at the time, and we made 1,000 amorphous metal distribution transformers and put them all over the country. Everything went swimmingly, so much so that in 1988, GE built the first commercial facility to take the metal we cast here and to make the transformers. And Allied Signal followed a year later, 1989, with the first large-scale amorphous metal casting facility, which is right where I am now in Conway, South Carolina, near Myrtle Beach. And even to this day, those casting lines we built back in '89 are the largest scale casting lines for amorphous metal in the world. Then in the 1990s, amorphous metal distribution transformers took off in the U.S., and this was followed by adoption in Japan, Taiwan, India, and South Korea in the early 1990s, China in the mid-1990s, Mexico, Canada, Brazil, Vietnam, and the Philippines in the 2005 to 2010 period, plus there are well over 20 other countries in the world that are in various stages of adoption, including South Africa, Chile, and several European Union countries. So concurrently with the development of the distribution transformer market, Metglas developed a line of nickel-based. Now, the transformers are iron-based, but we also developed a nickel-based amorphous alloys for use for metal joining, or we call brazing material. We call it Metglas braze foil. And this started from the mid-1990s when technology came out of Scandinavia to replace the traditional shell and tube heat exchanger with something called a brazed plate heat exchanger, which was much smaller in size, used a lot less material. So today, this type of heat exchanger device is very popular in automotive world for things like exhaust gas recirculators that are used for emission reduction. The metal joining product line will be a focus of a later podcast.
Can you tell us more about Metglas's evolution as a business?
We started out as a business unit of Allied Signal in the early 1970s when we were going through the development of the alloys that ultimately first came out for the transformer market. We were part of Allied Signal until 1999 when they purchased Honeywell, and we became Honeywell because Honeywell had a better name for brand recognition. So we were Honeywell from 1999 to 2003. And we were the only metals business at Honeywell, and they didn't really understand us. And that led in 2003 to the purchase of the Metglas unit of Honeywell by Hitachi Metals. So we've been part of Hitachi Metals when they purchased us, we had 2 casting lines here in Conway, South Carolina, capable of producing about 30,000 tons a year. Now, between here and Japan, there are 7 casting lines, and being able to produce about over 100 kilotons of Metglas amorphous metal per year, which is about enough to serve 10% of the global market. So we've expanded tremendously. We're always looking maybe to expand further, and depending on the market conditions. Globally, many countries, such as the United States, almost taking the lead here, have passed minimum efficiency standards for transformers. This is in the U.S. It was done by the Department of Energy. It was in 2 stages. The second one will come into play in 2016. And the world is seeing the advantages of efficient distribution. You know exactly what you're going to get with a more efficient transformer. You can calculate it, and it won't be wrong, and you'll know exactly how much CO2 you're going to reduce and what your payback times will be on the transformers. So that global trend toward more energy efficient electricity distribution is a wave we're riding, and it's going very well for the business, and we think we are helping them reach their climate change goals.
Can you explain how the unique structure and features of Metglas amorphous metals help companies increase application efficiency?
Sure. There are really 2 things in amorphous metal in the world of the distribution transformers that make it a very efficient material for distributing electricity. The first is the fact that it's amorphous. It's got that random crystalline structure that we freeze in at 1 million degrees a second when we cast the material. This being amorphous lowers something called the hysteresis loss. The other element that causes the energy efficiency, it's very thin. It's, again, about thousandths of an inch thick. And we compete against what we call traditional silicon steels, cold-rolled, grain-oriented electrical steels. Those things are at least 7 times thicker and sometimes 10 times thicker than what we make, because we cast it in a one-step process, whereas they start with a sort of a slab of material and they roll it down to a thin material, and it gets very expensive for them to go much thinner than they are today. So being thin lowers a second component of energy losses called eddy current losses. So we're amorphous and we're thin. So if you have a distribution transformer, when it's sitting there, even with no load on it, it's burning energy. It's actually taking electricity from the grid. Those are called no-load losses, and they're 24 hours a day, 7 days a week. They're always sort of like standby power. With amorphous metal as the core material in a transformer, that transformer will use about 60 or 70% less energy losses. It'll run cooler than traditional transformers. So it's all about energy efficiency. And of course, if you're not losing so much electricity and energy in the transformer at the end of the grid, to deliver the same amount of electricity, you don't have to generate as much. So one of the best features of amorphous metal is that with less generation, there's less CO2 emissions and other kinds of emissions, and that is really a very important selling point to ministries of power around the world and utilities that have sustainable goals, CO2 reduction goals. Metglas-based amorphous metal transformers can help them meet those goals.
Can you describe how amorphous metals are able to contribute to sustainability efforts, and how this technology can be further integrated for greater effect?
I think the best example is China. China has made a commitment to use amorphous metal for 50% of their transformers going forward, and they're honing in on that number today. And they're doing that solely to reduce the CO2 emissions in China. And they've got a lot of coal burning there. So we can help them meet their sustainability goals by this more efficient distribution of electricity. And China and India are 2 of our biggest markets. We're sort of an anomaly in the world here in the United States, South Carolina. Well over 60% of what we cast here for the transformer market actually is exported to India and China and other countries around the world. And we're doing And this is not just for the sake of efficiency at any cost. If you look at the energy savings and what we call total ownership cost, or also called total cost of ownership, depending on who you're talking to, there was a very compelling economic argument for using amorphous metal for ultra-efficient transformers. So beyond the emission reduction and CO2 reduction goals, there is an economic imperative to use things like amorphous metal for very efficient transformers. Also, just recently in the last month, Lawrence Berkeley National Labs, they did a study of the APEC countries, this Asia Pacific Economic Cooperation, not including China, and this number may or may not make sense to people, but it says if those 20 APEC countries were to convert to ultra-efficient transformers, such as that afforded by amorphous metal, the world would see 127 fewer million tons of CO2 generated over the next 15 years due to the lower amounts of generation required to deliver the same amount of electricity.
Looking forward, how will the developments Metglas is making with this technology affect key end applications such as electrical distribution transformers?
We are working on some new alloys that have slightly different chemistries that will allow our customers, which are the transformer manufacturers and people that make cores for transformers, to make a smaller core, less conductor, that's the aluminum or the copper that goes around the core, making a smaller, cheaper unit. So we're looking at new chemistries to improve the size equation for transformers. We're also looking at some nanocrystalline alloys that will have some nice applications in electronic components around the world. So we're continuing to develop new products. On the metal joining side, we've got some that melt at a lower temperature, allowing customers to use a belt furnace instead of a vacuum furnace, a continuous furnace instead of a batch furnace, because that's what they've got installed in their facilities. So a lot of alloy development going on the metal joining side as well. And then we're always working on productivity improvements here to get our costs down to help the whole cost equation throughout the supply chain.
Thank you so much for taking the time to speak with us today, Dave. For more information about amorphous metal technologies, visit Metglas at www.metglas.com.